Hi everyone and welcome to this new video. In this video we analyze another CVE. Specifically in this video we analyze a CVE 2024-4577 which allows to obtain remote code execution via PHP-CGI. And here I've created a testbed, and in this video I will discuss how to create this testbed. In this testbed we're going to install XAMPP because it's a simple way to get a PHP server up and running in Windows. Now, this Windows installation has a specific thing in which the character code is actually Japanese. So it uses the Japanese characters, and here you can see, because we don't have the slashes, but we have these other characters. And we can check which kind of character codes we are currently running with this code, with this command, console output encoding dot Windows code page. It says 932 because it's the Japanese character code. Now we have this XAMPP, we can go into the XAMPP server here, we can go into the PHP info page, which tells us that it's running version 8.1.25, which is one of the vulnerable version. Now, what can we do in this setup? Let's say that we have a XAMPP running with Apache, and we have this version of PHP. Well, if the PHP-CGI is enabled, as it is in this case, like if you go into the config and we go into the httpd.xampp.conf, here we can see that the CGI here is actually enabled. Now what can we do? Well, we can actually obtain remote code execution, and the payload that we will analyze in this video is the following one. You can see it down below. It is a curl that sends a post request to our virtual machine with this particular argument. And here we have the final payload that we will execute. It's a simple system calc.exe payload. So we execute it, and look at this. We have spawned a calculator. And in this video, we will analyze this vulnerability, how it works, how the payload works, and things of the sort. As always, I hope the video is going to be useful and interesting. If you have some feedback, leave it in the comments, subscribe to the channel, share this video and my channel with like-minded people to help me grow, and that's it. Enjoy the video. So first things first, right the day that I started to record this video, actually, the researcher who found this vulnerability, this CVE, published a very cool blog post, which I suggest you to read it, and we will actually read it together, at least the first portion. So this research was done by Orange Tsai and Splitline. They are very good researchers, and I actually listen to both of them at different conferences. Orange Tsai I listened 2 times at Romac, and Splitline I listened once on Molecon in Turin, both conferences in Italy. So very good researcher, you should follow their work. So let's try to understand the attack. Here I brought some notes, and also we will read the blog post by Orange. So essentially the idea is that this is the description of the CVE from the NIST advisory. So when using Apache and PHP-CGI on Windows, if the system is set up to use a certain code pages, such as the Japanese code pages, Windows may use BestFit behavior to replace characters in command line given to Win32 API functions. PHP-CGI module may misinterpret those characters as PHP options, which may allow a malicious user to pass options to the PHP binary being run, allowing to achieve RCE. This vulnerability affects the following version of PHP installed on the Windows operating system. So we go from 8.3 to 8.3.8, 8.2 to 8.2.20, 8.1 to 8.1.29. So that's the idea. In this case, this was 8.1.25. So 25 is less than 29. So this is a vulnerable version essentially. So what's the idea here? There's a lot of things said in this description. Let's try to understand it. So first of all, here we have Apache and PHP-CGI. I mean, this vulnerability has to do with how essentially binaries are called in Windows. And specifically in this case, it was the Apache program that was used to run the PHP binary. So it's a combination of Apache and PHP-CGI. So the operating system is Windows, so this does not affect Linux because essentially this vulnerability has to do with this BestFit behavior that is implemented by Windows that has to do with conversion between different character sets. And we will discuss essentially what BestFit means. So Windows is vulnerable. Not only that, not all character codes of Windows are vulnerable. Only if you run with Japanese and I believe it was a standard Chinese, traditional Chinese, another Asian essentially language code page. So only with certain code pages you would be vulnerable. Very, very interesting. And essentially, what's the idea here? Well, the idea is that there are different software here involved. There is essentially the Apache, and then there is the PHP binary itself, right? And with PHP-CGI, it's the bridge that connects Apache to the PHP binary. It's the way that through, like, you can run a PHP executable with user input through the PHP-CGI interface. And the idea here is that if you give certain characters to the Apache web server, the Apache web server will not consider those characters malicious. But then, when there is this change of processing, essentially, when there is this change of control between the web server and the PHP binary, those characters are actually converted into other characters. So on the level of Apache, we have Unicode characters, but then on the level of PHP, we have ASCII characters. And during this conversion, essentially, a character is transformed to the dash. And this allows to introduce options to the PHP binary being run, and when you can have control over the options with which you call the binary, you get code execution. So a malicious attacker can use this ability to obtain directly RCE. And indeed, if you analyze the payload we just used, the most important aspect of the payload, which we'll analyze in depth later on, essentially, it is this character, this %AD. Now, this character in Unicode means something, but then when it's transformed to ASCII, it means a simple dash. And so this is what allows to introduce the dash D and then the other stuff. Essentially, so this is the entry point for the attack. Once the attacker is able to introduce this character, the game is essentially over and the attacker won. So why does this %AD is transformed to dash? Well, that's what we will analyze. So how can we set up a vulnerable testbed to check this vulnerability? So the first thing we have to do is we have to set the system to the Japanese locale. And we can do this with set Windows system locale JA-JP. So that's the idea. And then we have to restart the computer and we should check that this actually happened with this command. And we can also see it because the slash are transformed into this other Japanese sign, the Japanese character, essentially. So that's the idea. Then we can download a vulnerable version of XAMPP, which contains both the Apache web server and also the PHP instance. And out of the different version, we can download the one that says PHP 8.1.25. So essentially this one. So you download this one, it's about 150 megabytes. And then once you have the installer, the executable that contains the installer, you can check the hash, the SHA-1 hash of the file, and it should be equal to this 515, and it should end with EF4. And I can take this into the directory in which I have downloaded essentially this thing. So here it's this essentially, where is the XAMPP? This one, XAMPP Windows blah blah blah. So I just do this get file hash and it takes a little bit and then I get 515E4EF4. So you can check the hash just to make sure what you're installing. During the installation process, install only the Apache and PHP components, because essentially there is a little menu, like let's try to click on it maybe. So going to downloads and going to the Apache Windows here. I say yes, let's install it. And of course you have to wait a little bit. Welcome to the installer. Okay, I have UAC, I don't care. And then so here you have to just uncheck everything else because what you need is already the default, which is Apache and PHP. I mean, those two make the vulnerable chain. You don't need anything else. It's gonna save at space. Here you select a folder and then you install it essentially. So like, let's say for example, a different folder. So let's download it into not Leo, but let's do QuickEmu. Let's do downloads and let's do XAMPP2 actually. Let's do XAMPP2. Of course, he didn't really understand it. Let's do it again. So user, QuickEmu, downloads. Here I've already installed XAMPP, but actually let's make it XAMPP2. So like a new testbed. So I do next, language English. I do next, and then we wait for the installation to take place. So at this point, we have installed the new version of XAMPP. We can close the old one because we don't care about that. And it says, you want to start the control panel now? We say finish. And this is the new control panel. So that's it, yeah. Now, the last thing that we need to do to actually make the testbed vulnerable is we need to change the configuration of the Apache component, and specifically the file http-xampp.conf, and we need to enable the PHP-CGI. So we go into config, we go into the third Apache, so httpd, http-ssl, and then we have xampp.conf, this one. And notice that the conf currently has comments, so it's not really valid, it doesn't really work, so we need to uncomment it. So we remove the comments here, we save it, and that's it. We start the server, and now we have, it says allow access, of course, the first time. So we say allow access, and now we have our vulnerable testbed, which means that if we execute the same payload as before, each should work again on this new testbed. And notice a new calculator has just been spawned, because here, essentially here we can control the command we give to the operating system. It could be a calc.exe, it could create a file, it could start a reverse shell, it could inject some malware. A lot of things could happen essentially at this point, because we have the basic primitive of code execution, which is very, very good. So that's it, yeah. This is how you create a vulnerable testbed. It's actually very, very easy. Now, how does it all work? Now here I had written a little bit of stuff, but since Orange Tsai actually published a blog, I would say let's go and read the blog, and then we will go back in this section to understand the command itself, so the final payload itself, because in this blog post he actually explains very well the idea. So let's read the blog post. The research unveils a new attack surface in Windows by exploiting BestFit, an internal charset conversion feature. Through our work, we successfully transformed this feature into several practical attacks, including path traversal, argument injection, and even RCE, affecting numerous well-known applications. Because the idea is that the same feature, which is this BestFit, not only can be used to obtain a CVE-2024-4577, which is the RCE in PHP-CGI, but it's actually used for different things, for file name smuggling, for environmental variable confusion, for argument splitting, and for the CVE that we are analyzing right now. So the story is much more complex, and this, after all, represents a new attack surface area. This technique was already known, but they applied it to Windows. They discovered this, they use this BestFit feature to use this technique, which is extremely interesting. So let's try to understand more about this BestFit feature. Now, if you are a Windows user, you are probably aware that Windows operating system supports Unicode. This means we can seamlessly put emoji, accented letters, fancy symbols, and other symbols, like for example here I do not have all the character codes, so they are not rendered properly, but the idea is that Windows supports this kind of stuff. Well, how does Windows manage the conversion between ASCII and non-ASCII? So how does it all handle? Well, essentially is that we start from ANSI, so historically ANSI was the first supported, then there was the introduction of UTF-16, and then recently there was the introduction of UTF-8. Since May 2019 is still in beta phase. So Windows initially used ANSI encoding, and ANSI encoding relied on code pages such as the one shown above. So for example, traditional Chinese is 950, Japanese is 932, which is the code we obtain in our PowerShell here. Like if you go up 932, output encoding Windows code page is the Japanese. So it used 8 to 16 bits to represent a single character. While these mappings were effective for certain languages, they were unable to accommodate mixed or universal character sets. So if someone wrote a text using a code page and then he sent it to you and you had a different code page, you were probably unable to render all the characters. So that's the idea. Now, Windows actually uses two different types of code pages. Here it says ACP, ANSI code page, and OMCP. So the research focuses on this type of code pages, so ANSI code page. So to check which ACP you're using, consider these methods. And this is the command I showed. I took it from this blog post. So console output encoding, we copy this, we put it here, and we will obtain our 932 essentially. So we copy this, we do this, 932. So additionally, you might also have heard of CASE-CP. However, be aware that CASE-CP displays the OMCP rather than the ACP. So be careful about which code page you're using. They are referring to ANSI code page, AACP. So initially there was ANSI with these code pages, then there was Unicode. So to address the limitation of code pages, Windows transitioned to Unicode in the mid-1990s. Now, unlike code pages, Unicode could represent characters from nearly all languages in a single standard, so very useful. And so essentially the most important one is UTF-16. Why not UTF-8? Because UTF-8, which is actually the most popular one nowadays, is actually still in beta and is not available for all the different languages. So that's the idea. Now, when you have different kind of encodings, of course, the idea is that, okay, but how do they all live together in the same system? Because even though Unicode became the backbone of Windows, Windows still needed to do what they always do, backward compatible. So they needed to support older version of the operating system. So they still need to support the old ANSI code pages. And to achieve this support for old encodings, Windows implemented two different versions of the different APIs. APIs that deal with ANSI and APIs that deal with Unicode. So for example, you might have the get environment variable A, and this is the essentially API that deals with the ANSI encoding, or with W, which is the API that deals with the Unicode encoding. So this approach allowed the developer to easily obtain their desired data format by simply switching between the A postfix and W postfix APIs. Of course, in this conversion, it's important to understand where we are coming and where we are going, because the idea is that if I start with a string that is already encoded in UTF-16, then going into UTF-16, that's pretty easy. That's like no problem. If I start from ASCII, going into UTF-16 is also pretty easy, because UTF-16 is actually bigger than ASCII, so it includes all the possibility of ASCII. Now the real issue, however, is what if we start from UTF-16, so we have a string that is encoded in UTF-16, and then we want to transform it into an ASCII string. Now in this conversion, we actually have to lose information. We cannot represent everything, because the space we're coming from is actually much bigger than the space we're going. ASCII is much smaller than UTF-16. So how can a wide character UTF-16 string also be in the ANSI format? Aren't they fundamentally different? So let's explore an example. Imagine we are on an English system with an environment variable env equal hello stored in the system. The data is internally stored as UTF-16, but we can retrieve it using both Unicode and ANSI APIs. So with the Unicode API, we obtain hello. With the ANSI API, we also obtain hello. But if you check the bytes, with the ANSI, we get 1 byte per character. So for 8, 65, 6C, 6C, 6F. With Unicode instead, we obtain 2 bytes per character. And here the LE in UTF-16 LE stands for little endian. It's just one of the ways in which you can store sequences of bytes. You can do either big endian or little endian. And notice here that the second byte here, it's always 0 because it is not used, because in the hello we use ASCII characters. So for the Unicode API, there's no problem Unicode in, Unicode out. No conversion needed. For the ANSI API, Windows applies an implicit conversion, and this is done by calling these two functions to convert the original Unicode string into an ANSI string. Now, since the hello consists of only ASCII, everything is fine. But what happens if the environmental variable contains a more complex string, like this one, with square root, pi, less than, infinity, and stuff like that? Well, if we use the Unicode API, we obtain, of course, this thing. If we use the ANSI API instead, we obtain this other thing, which is very strange. So essentially, it is this bizarre transformation at the heart of the CVE we are analyzing today, because this transformation is known as BestFit. So the original string is transformed into nonsensical things because essentially they try to transform each character into the closest looking character into ASCII. In Windows, BestFit character conversion is a way that the operating system handles situations where it needs to convert characters from UTF-16 to ANSI, so going from a big space to a small space. For instance, the infinity character symbol isn't part of the code page, so Microsoft decided to map it to the closest character, which is 8 actually. There's no strict formula for BestFit. Microsoft Do is more about making the characters look or even feel somewhat alike. So that's the idea essentially. So by using this feature, they were able to obtain many different results, including CVE-2024-4577. So this represents the first WorstFit attack, and it allows to compromise any PHP-CGI server configured with Chinese or Japanese code pages. Now, the affected code pages for this vulnerability are the Japanese, the simplified Chinese, and the traditional Chinese. So 932, 936, and 950. And the threat characters, the one that enable this thing, is the Unicode character 00AD. So the idea was that back in 2012, a vulnerability was found in PHP-CGI, and the vulnerability was that Apache automatically treated the query string as the first argument for the CGI program. So if you just appended to the query string dash something, that would be given to the PHP executable through the CGI interface. So of course this quickly led to RCE, it was patched, and the fix was simple. Stop parsing arguments if the query string starts with a dash. And notice what they do here. Here they check literally for the dash, for the normal dash. So the bypass they found is that instead of appending the dash, they append this character, which is not a dash, but it is transformed into a dash by the BestFit mechanism. And so with this, they were able essentially to discover the bypass and the RCE again. So in the blog post, they go over different types of techniques. Maybe we can treat them on different videos. For now, I just want to focus on the CV. So we go back to my notes. And so essentially, that's the idea. So here we can see different point of views depending on who is seeing the data. So what the browser sees is this thing. So the browser sees the Unicode character in the URL format. What Apache sees instead is the soft hyphen. So this thing looks like an hyphen, but it is really not an hyphen. So for example, in this case, this is not really a dash, it's a soft hyphen, it's the AD character in Unicode. And then when this thing is actually passed to the executable, so what PHP-CGI actually sees is that this character is transformed thanks to the Windows BestFit behavior into a simple dash, which represent an option for the binary. And so essentially we're able to execute like the code, the remote code execution, because there are these three different levels. I mean, here is the same thing, essentially just different representation, but the BestFit happens between when the Apache does the check, it does the check based on the Unicode, but then the Unicode is transformed into the ASCII, and at this point we have our option, because the ASCII is a dash, and then we can add our options to the program essentially. And to check this behavior, we can simply give here to the query string %ADS, and notice here we get the code itself, because when we run PHP with the -s, we're actually saying print out the code. And with this, of course, we are injecting this option into the executable itself, because the check is implemented based on the ASCII. So the check is implemented based on the ASCII, but we are passing the Unicode, but then this Unicode is transformed back into the ASCII. So that's a very fun attack. So to end the video, let's now understand how to transform the ability to introduce arbitrary options to the PHP executable into an actual RCE. So the idea is that in this case, we have a curl that does a post. So in the URL here, we have the IP address. So this is typical where we have a vulnerable host. And then we have the actual payload itself. And then we have this -d, which represents the body of our post request. So the post request is onto this URL, this one that we see here. And the body of the post is this PHP payload. So this is classical PHP payload. It's not really that interesting. What is interesting here is this section of the payload. So of course the arguments start with %AD, which our injection point. It is a Unicode which then gets transformed thanks to BestFit into the dash. So this is the best fitted character. Then we find an option, so we do -d, we put allow URL include 1. This will allow us to use the PHP stream wrapper such as PHP input, so it's going to be needed later on. Then we do auto prepend file PHP input, and this tells the PHP interpreter to read post data and include it into every script. And finally, we have the body itself of the query, which introduces the data we want to include into every script, which is the PHP system calc.exe. So that's the idea. We put a little bit of space and we're good. So essentially here we're passing an option to do the allow include so that you can use PHP input. Another option to say, hey, into every PHP file, include this thing, this thing that comes from the raw post data. And then we put the raw post data with the PHP stuff. With this thing, we're able to inject into the PHP context arbitrary code. So it's a very cool technique that you can apply every time you can control the options to the PHP executable. And here I will put into the description these references that I used to understand this vulnerability. It's a very fun vulnerability with a simple POC, which of course increases the impact, because when things are simple, they are also dangerous because everyone can exploit them. Of course, in this specific case, the funny thing is that to be exploitable, you need to run certain code pages, such as the Japanese or the Chinese, which is very funny because, like, if you are an English speaker user or another country, Italian, whatever, you're not vulnerable to this thanks to the actual code pages that you're using. If instead, of course, you are a Japanese user, then you must patch your systems, especially if you run PHP applications. So this is it for this video. I hope it was interesting. I hope it was fun. Give me some feedback if you have some, share this video with like-minded people, subscribe to the channel, and to the next video.